This video is a brief introduction to sequences. A sequence can be thought of as a list of numbers written in a definite order. Those numbers we call terms of a sequence, and they're commonly denoted by A1, A2, A3, and so on and so forth. Where A1 is the first term, A2 is the second term, and so on and so forth. And right here we have the nth term, or it's also called general term. And all of those are terms of a sequence. In other words, the subscripts that we see here, they denote the position of each term in the sequence. Well, a sequence can also be viewed as a function, and that's how it's going to be written: f of n equals a sub n. So for this function, all the inputs, or I can also say values of the independent variable, are natural numbers. Natural numbers, so these are numbers 1, 2, 3, 4, and so on and so forth, right? Natural numbers. And the outputs are terms of the sequence. So for example, f of 5 represents or equals to the fifth term of that sequence, whatever it is. And for that reason, this is how a graph of the sequence is going to look like. It's a discrete function, right? So it just consists of dots that we're not going to connect with the line. The horizontal axis represents n, and then the vertical axis represents terms of the sequence. A sequence can be described in a few different ways. One of them is just basically writing out the terms of a sequence. So here's an example. So that's the list of numbers. The first number represents the first term, that's A1, then the second term, the third term, and so on and so forth. And here's the nth term, of the sequence. And it's expressed as a formula, right? So in fact, sequence itself can be described by giving a formula for the nth terms, and that's going to be enough, because having a formula for the nth terms is enough for us to recreate all terms of the sequence, right? So then we don't really have to see that list unless we need it. So let's check this formula. For example, okay, so I have the fourth term over here, right? A sub 4, and according to this list, it's 5 over 81. Well, let's check. To find the fourth term of the sequence using the formula, I'll just have to find a sub 4, and then the subscript. Well, that's what n is. So if subscript is 4, it means that n equals 4. So to find the fourth term, I just have to plug in 4 for every n in this formula. That's going to be -1 to the power of 4 times 4 plus 1, and then divided by 3 to the power of 4. So let's simplify this. -1 to the power of 4, that's an even power, so it's just 1. 4 plus 1 is 5, right? So I have 1 times 5 in the numerator, and then 3 to the power of 4 is 81. Yeah, that's 5 over 81. That's what we can see here in that list. There are a couple notes that we need to keep in mind. So the first one is that n doesn't have to start at 1. And then note number 2 is that some sequences don't have a simple, or actually a lot of sequences don't have a simple defining formula like that. So even though we can see a list of terms, it's going to be either very hard or impossible to find a good-looking formula like that for many sequences. And finally, we're going to talk about convergence and divergence of the sequence. When sequence is approaching some number as n becomes large, so n becomes large means that we're moving further and further along the sequence. And as we notice that terms of the sequence are approaching some number, well, in this case, we say that the sequence converges. Or we can also say is convergent. And otherwise, in other words, if we move along the sequence and we see that terms of the sequence do not approach a number, specific number, then in this case we say that sequence diverges. Or I can also say the sequence is divergent. And this is something that's well illustrated if we look at the graphs of some sequences. Let's see. So right here, there is 8 examples of some sequences, of some convergent sequences. So see how terms of the sequence, they're approaching some kind of number here from below, right? They're getting closer and closer and closer to that number. So here's another sequence. Here I see its behavior. So how terms of the sequence are increasing, then decreasing, increasing again, but still getting closer and closer to what it seems like 0. Now here we have terms of the sequence. Well, if it's hard to read on this picture, but let's say if we consider that line to be 0, then we can see that terms of the sequence alternate. So it's positive, negative, positive, negative, positive, negative, and so on and so forth, right? However, terms of the sequence are still approaching a number. So, well, in this case, it looks like 0. Similar situation, now terms are not alternating, right? But there are some positive terms and negative terms, but as we move along the terms of the sequence, they are approaching same number. Here's an example of the constant sequence. So terms of the sequence are exactly the same, and well, it means that it's convergent. And a few more examples of convergent sequences. And now there's examples right here, 4 examples of some divergent sequences. So notice that terms of the sequence are increasing, decreasing, increasing, decreasing. They're not approaching the number, right? It's the same pattern that continues, and sequence is not approaching a specific number. Here we can see how terms of the sequence are increasing, and they just continue to increase. They're not approaching a finite number. They're actually approaching infinity, right? They're getting larger and larger and larger. So in this case, sequence is approaching infinity, and when sequence is approaching, terms of the sequence are approaching infinity, it's also considered to be divergent. In this case, terms of the sequence, they're kind of split into groups. So every other term would approach 5, and every other term would approach -5. So it means it's divergent. Terms have to approach one finite number to be called convergent sequence. And here terms are just all over the place. So it is example of divergent sequence.